So the finite difference method is the first thing that we're going to discuss. And we're going to do our first assignment only with the finite difference method. And let me tell you that this is the oldest method for numerical solution of partial differential equations, and it's believed to be introduced by Euler in the 1755 or something like that, very early. He actually did these calculations, of course, by hand at the time. The basic concept of the finite difference method is to just imagine Tailor series expansions. Well, you can use polynomial fitting, but Tailor series expansion is what we're going to use to explain it, to obtain approximations to the derivatives of the variables that appear in our partial differential equations. So the first step is going to be to discretize the domain. We need that. That's the first step. So the concept is to approximate derivatives using Tailor expansions. And the first step is to discretize the numerical domain by defining a grid. So here I have drawn a grid. This is a two-dimensional grid. So here's a possibility to introduce the nomenclature of a grid. So what is this? In finite difference, this usually means a locally structured grid. This is a structured grid. In fact, we call this a Cartesian grid, where each grid node, which are the little dots here, can be considered like the origin of a local coordinate system, okay? And the axis of that local coordinate system coincides with the grid. So the grid lines belong to some family of coordinate lines. So in this example of a Cartesian grid, of a structured grid, well, Cartesian means that Cartesian means that all of the intersections of different grids of grid lines are in right angles. Okay, that's Cartesian. But two lines. So if you imagine this to be like the origin of a coordinate system. Okay. Then this defines, here's in just 2D, defines two families of lines, okay? And grid lines of different families never intersect. And any pair of grid lines belonging to different family only intersect once. Sorry, same family do not intersect. And grid lines of different family intersect only once. So this is a Cartesian grid, where the Cartesian grid simply means that all intersections are at right angles, and we have each node identified by a set of indices, ij, in 2D. In 3D would be ijk, or something like that. And the neighbor nodes are explicit so again, for node, in this case ij is like the origin of a coordinate system. So from the point of view of node ij, we can identify all the neighbors by using these relationships I plus 1, I minus 1. Okay? So basically by increasing the index or decreasing the index, we get all the neighboring relationships. Now each node has one unknown value of the dependent variable and is also going to usually provide an algebraic equation for that unknown value. And that, let me see. So for each node we have an unknown value of the field variable, any field variable, and this one, which depends on the neighboring nodes. Okay, that's going to be the way that this whole thing operates. The nodes. And this provides one algebraic equation. Okay, this is the general idea. So, how does this work? Okay, I'm just wondering. So again, for the people who have done some numerical methods before, just bear with me. I just want to make sure everybody's on the same page. I don't want to insult your intelligence or anything. I just want to make sure that we're all understanding. So I'm going to do a very basic explanation of how this works. Okay, very, very basic. With a 1D example, in fact. 1D. So, remember the definition of a variable in 1D. A derivative in 1D. So, d dx is the limit when delta x tends to 0 of the function u at a position x plus delta x minus the value of u at x divided by delta x. Okay, that's our basic calculus 101 definition of a derivative. So what is the geometrical interpretation of this? Well, doing the geometrical interpretation of a derivative. It's the slope of a line, right? It's the slope of a function. The first derivative at a point is the slope of the tangent to the curve of the function. That's right? Represented by my little sketch here. So this is what I have marked exact. The slope of the tangent to the curve. Now the slope can be approximated by the slope of a line which passes through two nearby points. Okay? Let me show you. So here we have the point that is the point of interest, which I have called xi. And this line represents du dx. Right? Represents the slope of the tangent to the function u of x. So now consider 2 points nearby. This point here, which is point xi plus 1. And this point right here, which is xi minus 1. So analogous to our previous discussion of a grid, I'm just constructing a grid here, but in 1D, where a node of the grid is identified by a unique index I, and the neighbors are, I just add or subtract an index quantity. So I can approximate this slope by using a line passing through two nearby points. For example, one possibility is to use points xi and xi minus 1. If I use these 2 points, then I get what is called a backward difference. Use xi and xi minus 1. Okay, now I could also use the points xi and xi plus 1, and I get what's called a forward difference. And finally, I could also use xi minus 1 and xi plus 1. It's a possibility, and that's called a central difference. It's a very simple graphical introduction to the idea of differences. We use xi minus 1 and xi plus 1. So this sketch illustrates that some approximations are actually better than others. You can see that the line for the central difference, the other ones are kind of grayed out in the back, somehow seems to approximate better the slope to the exact line in this sketch, right? And you can see also, you can imagine that from my sketch, you can imagine that if I make the distance between these 2 points, which is delta x, smaller and smaller, you can imagine as well that this difference, right, will approximate more better the exact value. And that's another key concept as well of finite difference. So it is clear from the sketch that some approximations are better than others. And we'll see more about that. And the quality of the approximation improves as delta x is made smaller. Those are basic ideas that will survive. Okay, I continue with my very simple 1D example. And I will write down what those approximations are. You see, the backward uses the point and the point behind. The forward uses the point and the point forward. And the central uses the point on either side. Okay? So we're going to write those down now. Here's the exact. And then we want... so we're going to assume for simplicity that actually not necessarily the difference between xi and xi minus 1 doesn't necessarily have to be equal to the difference between xi plus 1 and xi. But for simplicity, we're going to assume that they're all equal, okay? So just assume that delta x is uniform, so that all of these distances are the same and let's write the backward difference. So we have what that's called a uniform grid in 1D. Backward difference is going to be the approximation of du dx by, we'll have u at xi, but I'm going to write that more short by just writing ui. It means u at xi minus u at I minus 1, because I'm going backward, divided by delta x. Just remember that for the exact, the only difference between this one and the exact had a limit when delta x tends to 0. So here we're forgetting about that. We're just writing what's inside the limit and assuming that delta x is quite small, so we can make this approximation. Forward, well, you can see what's coming. Du dx is approximately equal to ui plus 1 minus ui divided by delta x, and central is going to be approximating du dx by ui plus 1 minus ui minus 1. But notice that if this is delta x, the difference between I plus 1 and I minus 1 is actually 2 delta x. So this is divided by 2 delta x. right? All agree? So we're going to consider a Tailor series expansion for u of x in the vicinity of point xi. Okay, so u of x is equal to u of xi plus x minus xi du dx at, well, xi plus x minus xi squared divided by 2 factorial and the second derivative du dx again at I plus so on and so forth, the third, fourth, etc. until, let's write x minus xi to the power n divided by n factorial du, oops, this is the second order derivative here, so let's not forget that, and this is the nth order derivative, and even plus more, infinity to infinity. That's our Tailor expansion. So by replacing x by either xi plus 1 or xi minus 1, then we get the expressions for the variable values at these points, xi plus 1 and xi minus 1, in terms of the variable at xi and its derivatives, which is what we need. Okay, so let's consider the first one, xi plus 1. Let's do that one first. So this we're going to get u of xi plus or minus 1 in terms of u xi and derivatives. So let's pick the first one, xi plus 1, and so let's see, I'm going to do xi plus 1, so I'm going to have xi plus 1 here, and xi plus 1 whenever x appears, right? So I'm going to have uxi plus 1, I'm going to take this guy to the other side, so I have uxi plus 1 minus uxi, and I'm going to divide over by by this guy over here. I'm going to divide over by this guy I'm going to take to the other side, I'm going to divide over here to isolate the derivative, okay, the first derivative. So I'm going to skip those steps because you can see them clearly, and I'm just going to write the u dx at I is going to be equal to, and instead of writing u of xi plus 1, I'm going to write just u I or I plus 1, etc., right? So I'm going to skip the x to make it shorter so I don't write so much. So we have u here, I plus 1 plus 1 minus u I, this guy here, divided by, xi plus 1 minus xi. And we still have all of these other guys over here, right? So we have, minus, I'm going to put them all on the other side, so we've isolated the derivative that we want to approximate. So, with a minus sign, but we've divided over by 1 of the x minus xi, so I have only 1 here, xi plus 1 minus xi divided by 2 times the second derivative at I minus the one that involves the third derivative, which has xi plus 1 minus xi squared divided by 3 factorial and third derivative, because I've divided over by one of these, and, actually a minus, but it doesn't really matter, what we call higher order terms. Okay? You can see that if xi plus 1 minus xi is small, then all of this here can be neglected. The only possible problem, and this is something that most people forget, but there is still a possible problem. The only possible problem would be if one of these derivatives was very, very large. Okay, so keep that in mind. If this one of this, but we assume that the functions are sufficiently well behaved that that doesn't happen. The derivatives don't blow up. Okay, and so if this guy is small, then we can neglect all of those terms. We neglect all the high order terms, and we get the forward difference. We get the forward difference approximation. But we neglected terms of which the biggest one is this one, because if this is small, definitely less than 1, then this one is even smaller. So the largest term that we neglected is this one. So we say that we neglected terms of order delta x. Well, delta x is this guy. You agree? And therefore, these are called the truncation errors. The truncation error. And the important thing to note is that as delta x tends to 0, the error tends to 0. And therefore, this approximation converges. So forward difference, I'm just going to write FD, converges. And this is a good thing. All right? Now we can do the similar work. You can see immediately how we can do the similar work for the backward difference and for the central difference. Okay? For the backward difference, we're going to get the same result, order x squared. But for the central difference, the error is order x delta x squared. Okay, so next class we're going to use this to start with our practical module. So this next class is going to be much more about examples. We're only going to do examples, okay? We're going to do the first, probably get to the first 8 or so, I think, examples, or maybe even all of them, of using these approximations for what are going to be the 12 steps to simulating the Navier-Stokes equation.